right, hi y'all. Today we're going to take a look at volumes of revolution when you revolve and the area completely meets up with the axis of revolution. You'll get what we call just a disk. As opposed to washers that we covered yesterday, that was if there was any space in between what you were revolving, you would create a washer. And so today we're going to look at disks. So this is basically just a special case of the disks. It's where you had no space or a special case of the washer, you had no space in between, and therefore you just get circles. You don't even have to worry about a hole in between. Okay, so that's what all of this is. Again, we're only going to be rotating around the x-axis or something parallel to the x-axis, y-axis or something parallel to the y-axis. And again here, this is the idea of a disk. If the entire area of the region meets up completely with the axis of rotation, then after you rotate it, right, each cross-section of the remaining solid would be a circle, right, which I call a disk. And I always go back and forth whether it's supposed to be a C or a K, but disk. And that has an area formula, obviously, of just pi r squared. Right? So if you can imagine, like if you take a slice and you rotate it around and that entire area was meeting up with the axis of rotation, that would just be a big old circle, right? If you sliced it perpendicular to the axis of rotation. I do have a fun prop to look at today. You may recognize, if that was the function and completely meeting up with the x-axis, if we rotate that around the x-axis, right? There is the infamous Pokeball going all the way around, Pokemon ball. I don't know if I'm saying it right even. And if you were to slice it, right, each of those slices would indeed be a circle, right? So you can imagine we rotate around and then each of those slices would just be a big circle. We'll talk about the radius being that distance, right? So a circle, a disk is just a circle with one radius. All right, hope that makes sense. Let's take a look at our few examples. So we've seen this exact same function a few times now. I think we found the area in part in 9.1. I think in 9.2 we found, that this region had certain shapes popping out at us so we could find the volume of that. Now for this time, we're taking this same function. The f of x is that to the fourth power, and the horizontal line y equals 4. It says find the volume of the solid generated when r is rotated around the line y equals 4. So we're taking this region and revolving it right around this line y equals 4. Okay. Well, because the region meets up with the axis of rotation the entire time, that's how you know it's a disk, right? So we're rotating around here. If you can imagine, it kind of will look like a big old sideways Hershey's Kiss, if you can imagine that. And we're going to be slicing it this way. So that would just be a circle. There'd be no holes in between. So it's going to be a disk. So as soon as you notice that your axis of rotation meets up completely with the area, you have a disk. And so I'd be like, okay, the area of every disk is always pi r squared. Okay. Then you think about the volume of one of those disks, right? I do have my, so there was the area, right? I'm sure you can't see, but if you turn on its sides, like a slight thickness to this slice. And so you can imagine that if you're going vertically, that will be a dx. If you're going horizontally, that will be a dy. So this will just be pi r squared times the thickness, dx. And then you're going to add up all your slices. So you're going to integrate. So here we go. The volume will equal pi times the integral of whatever our radius is squared with respect to x, no matter where we slice it. Again, that's the first thing you have to have written on your page. You don't have to have the area and the dv. I just like that to remind myself that I got to have that pi out in front and I have to square the radius. Okay, so for this problem, we've worked with it so much that I already remember what the points of intersection were. I knew they were crossing here at 0. And then when we set these equal to each other, because this was equal to 4, then when you set this equal to 4, the 4's end up canceling. And so you can factor out an x cubed, and you're left with x cubed times x minus 2.3. If you set those equal to 0, that's why this one was 0, and that's why this one was 2.3. So this point of intersection was exactly 2.3, right? Now, keep in mind, you're supposed to be accurate to 3 decimal places, so it kind of freaks me out when I say 2.3. If you want to not freak me out, you can write 2.300, but obviously you don't have to write the zeros because it was a nice, clean, exact decimal. If we had calculated that in our calculator, we'd want to, preserve all of the decimals. Okay? Okay, and then again, the radius on this is just like what we were doing with the washers. You can imagine standing on the axis of rotation, the furthest thing away is going to be the radius. And there's only one thing, right? So you're like standing here on the axis of rotation and staring furthest away in the original region. Oh, original region was down here, my bad. So we're staring in the original region, right? And so that distance would always be the axis minus the curve, the axis minus the curve, right? Axis minus the curve. So the radius is always the axis minus the curve in this case, which was f of x. And the axis was 4. So 4 minus f of x is what we're going to plug in here. And again, we were integrating from 0 to 2.3. So you could type that into your calculator, right? I tend to put my pi in there first. So I'll go ahead and model this since I have plenty of time. Let's see if the calculator will show up today. I think I already have this typed in, yeah. So y1 is my f of x. So I'll quit out of this and go second caret, which is pi, right? And then math 9, integrating from 0 to 2.3. And then inside here, because we're quantity squaring, we will need a new set of parentheses. So you'll want to like open set of parentheses. And then 4 minus vars, y vars, y1. Oh, and again, I had that 4 in there as y2, so I could have done y2 minus y1, right? Either way. And then quantities square that, all with respect to x. Nice, and if I've done that right, it should give me a 22.454. Nice. So 22.454. Looks like that was the only acceptable answer. Must not have. Oh wait, there we go. 454, and then a 3. So right, you truncate or round, it's the same answer. All right, I hope that made sense. Let's take a look at example number 2. They have a lot of language going on there. And in fact, for the problem that we're doing, we don't need all that language. But they told you that we have the curve f of x is 4x squared minus x cubed. And then you have this line, y equals 18 minus 3x. And then that line is tangent to the graph at x equals 3. It says R is the region bounded by this, and let S be the region bounded by this. The only question I'm asking you here is find the volume of the solid generated when R is rotated about the x-axis. So we're taking this R and rotating around the x-axis. It looks like I got to make this one a little smaller just so I can actually like draw the picture of that rotation. Right? So if you can imagine, if I'm taking this and rotating around the x-axis, it looks really similar to the problem before in that it almost looks like, you know, kind of a sideways Hershey's kiss, and that all of these would be just circles. Again, because region R met up all the way with the axis of rotation, that's how you knew it was a disk. Okay. So on this, I'd be like the area of every disk is always pi r squared. Right? The volume of one of those disks would be pi r squared times the thickness. Again, it's either going to be dx or dy every time. Because we're revolving around the x-axis or something parallel to the x-axis, and you always slice perpendicular, the thickness of that slice would be a change in x. So that would be a dx in this case. And we're going to add all those up. So the volume would equal pi times the integral of whatever my radius is squared, dx. Again, that's the first thing that you have to have on your page. So what I haven't found on this problem yet, right, was where I started, boom, and where I was ending, boom. So I'll need to find those points of intersection. And technically this time the points of intersection are with the x-axis, so those are really just zeros, right? So if I graph this and find those two zeros, it looks like when I found those zeros, they were nice and clean. This was exactly 0, and this was exactly 4. So not even a messy decimal. And then no matter where I slice it, right, if you're standing here on the axis of rotation, the furthest thing away from you was the curve. Every time it's just going to be the curve minus the axis, right? The curve minus the axis. So the radius was always the curve, f of x minus the axis, which was 0, right? So you could write f of x minus 0 or just f of x. Right. I'm going to go ahead and preserve the axis in there just in case we need it. Because I always want you to think of something minus something is the distance. And then we started at 0 and ended at 4. Yeah, type in that into your calculator, we get like a really large number, 490.208. All right, hopefully that makes sense. So far we've had lots of verticals. Guess what's coming up? So feel free to try to draw this. And I know my students always comment on how big these functions are. I'm not sure why f of x is so large. I'm not yelling at you. So if f of x is x squared, maybe you can sketch that, right? And then y equals 4, see if you can sketch that. And it said that R is the region bounded, notice it said in the first quadrant. So just in the first quadrant. Bounded by this, the y-axis, and y equals 4. So let's go ahead and sketch that. So I know y equals x squared is that whole thing, right? But we're only in the first quadrant. The y-axis, that's here, right? Jaune. and y equals 4. That's nice. So I'm going to go ahead and erase this left side because it said only in the first quadrant, right? And then here's 1, 2, 3, 4. So that's the area, right? Like section 9.1, we can find the area of that region. Now they said here that we are rotating this around the y-axis. Okay. So rotating around the y-axis. So I'm going to just draw this in here. This is where I'm rotating. So because we're rotating like this, you can imagine the mirror image look like this. And then all of our discs would just be, these circles, give a slight little bit of thickness. These would just be a bunch of circles, a small circle on the very bottom and then bigger circles up top. Okay, this is our first horizontal disc. So remember with horizontal, you have to do the extra annoying work that you gotta solve these equations for x. Okay, but I'll go ahead and just start writing my formula because I know it's a disc. I know that it's still gonna start the exact same way, that the area of any disc is always pi r squared. Right, the volume of one of those discs would be pi r squared times the thickness. And again, because we were revolving around the y-axis or something parallel to the y-axis, the thickness of our slices are going to be a change in y. Right? So the ever slight thickness would be a change in y. And we're going to sum all those up, so we're going to integrate. So it'd be like volume equals pi times the integral of whatever my radius is squared dy. And I got to figure out where am I starting, where am I ending. And remember, all of the problem, everything has to be in terms of y for this problem, right? So these need to be y values, so y equals and y equals, and these need to have y's in them, right? So the extra work you always have to do for horizontal is you're gonna have to solve for the left function, and you're gonna have to solve for the right function in terms of y, right? So solve for x. All right, so if we look at this, where are we starting, where are we ending? Remember, these are y values now. So we're starting down here at 0, right, and ending up here at 4. That's where we would slice. So our limits of integration are going to be from 0 to 4. And then if you're standing on the axis of rotation, which in this case was the x-axis, right, y-axis. So here we are, we're standing on the x-axis, y-axis, the furthest thing away from you, right, in the original region. So it would be right minus axis. So the radius is going to be the right curve minus the axis. And in this case, the left and the axis were the same, right? The left and the axis of revolution were the same. Those were both the y-axis. And the y-axis is just x equals 0. Okay, so I know I'm just going to be subtracting out 0 in this case. And then the right curve, remember, was this f of x equaled x squared. So that's the same as y equals x squared. And so we have to solve for x, so we're going to undo the squared by square rooting. Don't forget plus or minus. So x equals plus or minus square root of y. But remember, we were only in the first quadrant, so hopefully you're comfortable that we'd be looking at the positive values of those. So x would just be the positive square root of y. And so then when we go to plug in what our radius was, we were constantly the right minus the axis, the right minus the axis. So root y minus the axis, which was 0. So most of the time, these problems cannot be solved by hand because it's too complicated and you got it squared. But check this one out, y'all, because root y minus 0 is just root y, right? And then root y squared would just be y. We can do this one by hand pretty easily, right? So let's go ahead and have fun with this one. That this would be equivalent to pi times the integral going from 0 to 4 of root y squared would just be y. So anti-deriving y would get us to 1/2 y squared, and the pi was out in front, right? So pi times 1/2 y squared, evaluated from 0 to 4, and then plugging in 4 minus plugging in 0, right? So what's that? Pi over 2 times 4 squared minus pi over 2 times 0 squared. So obviously that 0 is going to 0 out. Don't always assume it's going to 0 out, right? Because if you have an e to the, it doesn't 0. But 0 squared, 0 times pi over 2, 0. 4 squared, 16 times pi over 2 would be 8 pi. Obviously, if we did it in our calculator, we would get a decimal approximation, and it looks like you get about 25.132. So approximately 25.132. Looks like I wrote down both, 25.132 or 33. Right. So this would be an example of a problem that could be in the no calculator section, because I'd expect you to be able to graph both of those. I'd expect you to be able to spin it around and set that up, and then actually calculate it without a calculator. Okay, so that could be in the no calculator section on this test. All right, and last but not least on this one, it looks like I'm having you do two different disks, same region. Letter A, you're revolving around the line y equals 6, and part B, you're revolving around the line, the y-axis, right? So this might be a good one for you to pause and try. I'll give you the hint that they are both disks, right? But one's vertical and one's horizontal. Okay, so I don't know if you can see that. Let's do part A. It says we're taking that and revolving around the line y equals 6. Right, so y equals 6 is that top horizontal line, right? I'm just going to resketch over here. So here's my region, and then I'm revolving right around that line y equals 6. So because there's no space in between, that's why I know that it's going to be a disk, right, every time I slice it. So these are going to be circles, but there's not going to be holes in between them. Right? So just area of a disk. So I'd be like, okay, the area of every disk is always pi r squared. Right, the volume of one disk is going to be pi r squared times the thickness. In this case, perpendicular to the axis of rotation, which was y equals 6, which is parallel to the x-axis. So we're going to slice it perpendicular, that would be a dx. And then you're going to add all those up. Integration. So volume equals pi times the integral of whatever my radius is squared with respect to x. Okay, so on this one, my limits of integration were actually kind of given to me, right? They told us that we were going from 0 to the x coordinate here is 9, right? And so I'm going to be slicing from 0 to 9. So those would be my limits of integration. And then no matter where I, look, if I'm standing on the axis of rotation and stare out, the furthest thing away is that curve, right? So I'm going to subtract the axis minus the curve, which was what, 2 root x? And the axis this time was 6. So 6 minus 2 root x is what should live in here for your radius. Okay. So if you have those typed in, as your y1 and y2, you could just say pi, math 9, 0 to 9 of y1 minus y2, or vice versa, quantity squared. Final answer on that, it looks like you should get 169.646. Okay, and that was a nice vertical slice because we were rotating around a line parallel to the x-axis. And then part B says find the volume of the solid generated when r is rotated around the y-axis. Okay, so now we're rotating around the y-axis. Hopefully you can see that we're rotating around like this, so now we're like, mirror image would be like this. And so our circles, still disks, right? Because there's no space in between the area and where we were rotating. So we know we still have a disk. Okay, so you're still starting off with saying that the area of a disk is still pi r squared. The volume of one of those disks is still just pi r squared times the thickness. But this time, we're rotating this way, so the thickness is going to be a change in y. So it's going to be a dy. And then we're going to add them all up. So now the volume will equal pi times the integral of whatever the radius is squared with respect to y. And then don't forget you have the extra work of changing the limits because they need to be y values and solving for x. Right? So let me erase my part B here. So part B was 0 to 9, right? This time we're talking about the y values, so we're starting going from 0 to 6 is the y value here, right? So the integral should be from 0 to 6. And then my radius, right? I have my left curve and my right curve. Anytime you do a horizontal slice, you have to solve for x, right? Because we were rotating around the y-axis, right? That was the left curve, and that's just the same as x equals 0. So it's already solved for x. And then the right curve in this case was y equaled 2 root x. So let's solve that one for x, right? Divide both sides by 2, so y over 2 equals root x, and then square both sides, right? So x would equal y over 2 quantity squared. And maybe I'll just simplify that and just say y squared over 4. So right minus left, right? It looks like if I'm standing here and I'm staring out, the furthest thing away would be the right curve, and I'd have to subtract out that axis of rotation. So the radius was always the right curve minus the axis. In this case, that was y squared over 4 minus the axis of rotation, which was 0. I don't know if that red pen shows up or not. So that would be your setup. And remember on this, you can't use your Y1 and Y2. You do have to type this in. You can use a dummy variable though. Right? So, this actually is one that we could do by hand, but because there's a pi, you can just leave it in terms of pi. But if you type this one in, you get 305.362. All right, y'all, I hope that made sense. Let me know if you have questions on your calculator and stuff. Okay, bye-bye.